Oil and gas operators routinely spend millions of dollars on heavy capital equipment with a singular, destructive purpose: to burn off localized liabilities. The King Abdallah Petroleum Studies and Research Center, or Kapsaec, operates an open-source energy data portal tracking these global emissions. Their data reveals the staggering scale of this practice, with operators flaring roughly 150 billion cubic meters of waste gas around the world every year. Managing this waste requires massive upfront capital expenditure, or CapEx. A traditional enclosed flare system requires between $1.5 million and $3 million in total installed costs, generating absolutely no financial return. That flared gas contains highly energetic chemical bonds. By combusting it into the atmosphere, operators are incinerating an estimated $7.5 trillion in locked material potential. The engineering solution to this inefficiency is the petroflash micronode. This is a localized material synthesis reactor designed to intercept the waste gas before combustion. Deploying this node flips the financial equation. It replaces a $3 million depreciating flare asset with a $275,000 modular unit. Instead of producing ash and carbon dioxide, the reactor outputs two product streams: clean hydrogen gas and turbostratic graphene. Turbostratic graphene is a specialized carbon lattice where the layers are randomly rotated, making it highly valuable as an industrial reinforcing additive. Because these wellheads are often located hundreds of miles from the nearest power grid, the system must achieve total energy sovereignty, generating 100% of its own operational power on site. This is the technical blueprint of the micronode. It operates as a fully decentralized, self-powering refinery in a box, built to capture a waste stream and process it into a profitable supply chain. The entire system fits inside a standard 20-foot wastewater treatment container, which costs a baseline of $1,500. Specialized external intake manifolds allow the container to be dropped directly onto existing concrete wellhead foundations, forming a direct, plug-and-play connection to the gas lines. Inside the container lies the operational core of the node, the flash chamber. This chamber is constructed from a high-purity quartz tube, engineered specifically to withstand instantaneous thermal shocks of up to 3,000 Kelvin without fracturing. When petrochemical feedstocks hit this temperature, they violently outgas and lose physical volume in a matter of milliseconds. To counteract this rapid expansion, servo-driven linear actuators push copper or graphite electrodes into the material. They maintain a continuous dynamic compression of 10 to 50 pounds per square inch, preventing electrical arcovers that would otherwise shatter the quartz. Inside this precisely pressurized, extreme temperature environment, the amorphous atomic structure of raw petrochemical waste breaks down and reconfigures into a highly ordered, crystalline graphene lattice. Reaching 3,000 Kelvin requires massive, instantaneous power delivery, supplied by a 400-volt internal capacitor bank with a total electrical capacity between 0.2 and 1.0 farads. The system fires in a dual-pulse sequence. First, a low-voltage alternating or direct current pulse preheats the feedstock, driving off residual moisture and beginning to crack the long-chain hydrocarbons. Next comes the primary flash discharge. The capacitors dump between 100 and 400 volts directly through the compressed material for roughly 10 to 500 milliseconds. This triggers electrothermal vaporization. Electrothermal vaporization is a process where intense heat forces elements with lower boiling points to instantly transition from a solid directly into a gas phase. This vaporizes all heavy metal impurities, leaving only pure carbon behind. Managing this violent plasma phase is the Nexus LIMS AI, which dictates the firing of insulated gate bipolar transistors. Insulated gate bipolar transistors are high-speed semiconductor switches capable of handling sudden surges of thousands of amps. The AI relies on a resistance feedback loop monitored by analog-to-digital converters. Analog-to-digital converters are sensors that translate physical electrical currents into digital data a computer can process. These sensors monitor the voltage and current precisely every 10 microseconds. If the digital readouts show the feedstock's electrical resistance dropping too rapidly, indicating a dangerous thermal runaway, the AI instantly commands the transistors to truncate the power pulse prematurely. By reacting to the material state in fractions of a millisecond, The software forces a chaotic, destructive plasma arc to behave as a predictable, scalable manufacturing tool. Extracting the solid graphene is straightforward, but the flash process violently ejects high-energy hydrogen and volatile hydrocarbons that must be actively managed. To control this, the entire recovery system operates under a slight negative pressure, physically pulling the expanding gases away from the 3000 Kelvin plasma zone. This diagram shows the first stage of recovery. The vapors are drawn through the porous electrodes and routed directly into a cryogenic cold trap. Chilled between -40 and -70 degrees Celsius, this trap forces light oils and naphtha-grade hydrocarbons to condense into a liquid, creating a secondary, commercially viable product known as flash oil. Stage 2 focuses on particulate scrubbing using an electrostatic precipitator. An electrostatic precipitator is a filtration grid that uses high voltage to statically attract and capture fine dust. The gas passes through this grid and a final HEPA-grade filter to remove microscopic carbon soot. Stage 3 maximizes the chemical value of the stream by pushing it through a pressure swing adsorption unit. Pressure swing adsorption is a mechanism that separates specific gas molecules from a mixture under pressure based on their unique atomic characteristics. The process splits the stream into two distinct outputs. A methane-rich tail gas is isolated and looped back to provide facility heating, while high-purity hydrogen, rated at over 99%, is cleanly extracted. Capturing these volatile elements neutralizes a serious explosion hazard, while converting the shipping container into a decentralized flash refinery. This continuous refining process demands intense electrical power. Driving a 400-volt capacitor bank repeatedly in the middle of an isolated oil field requires a dedicated power plant. That power plant is fueled directly by the high-purity hydrogen stream we just isolated in the gas recovery loop. To prevent the gas from degrading the metal over time, a process known as hydrogen embrittlement, the hydrogen is routed through specialized 316L stainless steel piping and fed into an internally mounted Bloom energy server. Inside the Bloom server, solid oxide fuel cells consume the hydrogen to continuously trickle charge the container's onboard 1 megawatt-hour battery energy storage system. A battery energy storage system is a high-capacity network of batteries used to hold electrical energy for continuous output. Because the system uses its own chemical byproduct as fuel, the operational energy cost of the entire micronode is exactly $0. The integrated Bloom server functions as a high-capacity battery that never requires an external charge, allowing the unit to process waste and synthesize materials off-grid indefinitely. When you pull back from the specific mechanics of a single container, the macroeconomic impact of deploying these nodes across thousands of isolated wellheads becomes clear. This chart maps the financial divergence. A traditional enclosed flare demands a $1.5 million capital expenditure and yields zero revenue. A single petroflash node costs $275,000 to deploy and generates between $1.2 and $2.5 million in recurring annual value. This intense capital efficiency means the hardware pays for itself in fewer than 90 days. To accelerate deployment, operators can utilize Bloom Energy's Series 10 option. This zero upfront model covers the equipment and installation in exchange for a flat 9.9-cent utility rate. Removing upfront hardware costs allows operators to preserve capital, redirecting funds into mass production of synthesis reactors at the Ukiah Gigaline facility. Scaling this decentralized network requires absolute safety at the edge. The system relies on automated argon gas purges, lower explosive limit sensors, and Class 1 Division 1 explosion proofing. Lower explosive limit sensors detect the minimum concentration of gas required to ignite, while Class 1 Division 1 is a safety rating for equipment designed to operate securely in continuously flammable environments. Mechanically, the node eliminates the methane slip common in legacy flaring. Chemically, it captures raw carbon and locks it securely into advanced structural materials designed to last for centuries. The oil and gas sector already spends billions of dollars to manage its flare gas. By redirecting that existing budget into the petroflash architecture, operators can convert a massive environmental liability into the most profitable advanced material supply chain in the world.